So my talk will indeed be about the history and quite interesting the Jesuit case. This theme of the last conference is between the relations between mathematics and non-mathematical public cultures, and I think the Jesuits have been quite successful in this respect in two areas, namely their missionary work in Asia, in which mathematics was often a tool to get access to the important people and structures there, and secondly the education system in Europe starting from the 17th century. Their interest in mathematics and their teaching of mathematics led to popularization of mathematics. They wanted to mobilize a larger audience for an interest in mathematics, and by doing so, by making it more accessible, they also this led to a process which we can call a physicalization of mathematics. I will give you some examples of that. Let us first start with the main goal of the Jesuit order. This is to convert people to Christianity, and the Jesuit order shares this with other orders, but specifically they do so by education of children and unlettered persons, including people outside of Europe. So one of the important goals they had is to convert people to Christianity in Asia, and they undertook several missions to do so. One of the founders of the order, Francis Savier, started on one of these first missions starting from Lisbon in 1541. And his goal was to reach China. They've been in India, Goa, Malaysia, the Philippines, Indonesia, China and Japan, but he never set foot on Chinese soil. He died, like many of these missionaries died before reaching China, and he died on the island before the coast of China. Later on, they have been quite successful both in China and Japan. In China, you have probably some names you heard of. Matteo Ricci, an Italian Jesuit, who was skilled in cartography and used this to get access to royal circles. He mastered the Chinese language and translated Euclid into English. The Flemish Jesuit Ferdinand Verbist was skilled in many areas. He cooperated in the reform of the calendar and astronomy. He became head of the observatory in Beijing. He designed all kinds of instruments, and the Chinese especially liked his interest in military machines. And then another name, which is quite important later on, is Antoine Thomas, also from the Belgian province, as he taught mathematics, including algebra, to the Emperor Kangxi by the end of the 17th century. In Japan, they were less successful, though they were able to convert a large number of people to Christianity. In Japanese it's called Kirishitan. And by the end of the 16th century they converted about 200,000, mainly on the island of Kyushu, where Nagasaki is located, including several of the lords, the daimyos. But also they had a practical interest. The Jesuits gave them easy access to saltpeter. But this conversion became a problem for the Tokugawa regime, which was established at the beginning of the 17th century, and the Jesuits were expelled in 1614. This led to the closure of Japan, the so-called Sakoku policy, and which led to they all had to leave Japan. Only the Dutch were allowed for trade missions in an artificial island before the coast of Nagasaki. Those that stayed were prosecuted. They were tortured to commit apostasy, or they were killed. And here's a Latin book describing the death of Antonio Francisco Cardim, who did not commit apostasy. Also other friars from the other orders, Augustine and Dominican, were killed. As an illustration of their determination, despite the closure of Japan, they still undertook another mission in 1643, the so-called Rubina group, which is, the story is told in a novel which is quite popular in Japan by Endo, and It's rumored that Martin Scorsese bought the rights and will turn it into a movie this year. The main successes were, of course, in Europe. The education system was vastly expanded in the first century of the Jesuit order, up to 444 colleges, including several universities. The first university was the Collegio Romano in Rome, with important names like Christopher Clavius, Kircher and Scott, and students who studied there, Gouldin and Valerio. There is also the bibliography of all Jesuit writings by the Bakker and Sommervogel, and during the first 2 centuries they list no less than 631 authors who wrote on mathematics in the broadest sense. So a lot of Jesuits were involved with mathematics. And their education system produced many men of science and mathematics, which were either Jesuits themselves, like Biancani, Honoro Fabri, Grimaldi, Scheiner. This is only the beginning of the 17th century. But others were educated at Jesuit colleges, like René Descartes at La Flèche, his friend Claude Midorge, Mersenne, Marquis, Cassini, and so on. Europe was divided in several provinces, and I will mainly talk about the Champagne and the Flandro-Belgian region provinces. So, by the end of the 16th century, they formalized their education system in several layers, organizational layer, and the legal issues. Also, the content of the way the lessons were organized. They were organized in several sections. First, you had lectures, lectio, in which the teacher taught the material. Then the students rehearsed it in so-called repeticiones, and then on a weekly basis they held disputaciones with a proponent and an opponent discussing all kinds of things. Concerning mathematics, this was mostly an application or discussion of problems to other domains. And these disputaciones had often a public character. So not only was it for people from the college or university, but also external people were invited to attend this, and they had a quite theatrical aspect. And these regulations were published as a book called the Ratio Studiorum, the final version in 1599, and it was also established that every college and university had to appoint a professor of mathematics, which was quite new at the time. The Ratio Studiorum describes some of the tasks of this mathematics professor. In the beginning there were no chairs, but then mathematics was taught by the philosophy professor. And those who showed an aptitude for the discipline of mathematics should be pursued by further instruction, private instruction, to get more involved in mathematics. It also shows that maybe mathematics was not the most popular subject, so it should be connected with other subjects which were more popular with the students, like geography and astronomy. And here it describes how to do these disputaciones, for example, discuss a famous or celebrated problem in the presence of a large gathering of students and even people outside of the colleges. The content of mathematics was much broader than we now consider as mathematics. You had on the one hand pure mathematics as taught in the quadrivium, arithmetic, geometry, music and astronomy, but Jesuits were more interested in the so-called mixed mathematics. The term starts to appear in the 16th century, but goes back to the idea of subordinate mathematics from Aristotelian writings, and it becomes transformed again by the beginning of the 17th century in so-called physico-mathematics, the preferred term by Beckmann, Mersenne and Descartes. And it included subjects like mechanics, optics, perspective, statics, hydraulics, meteorology, ballistics, fortification and navigation. And these were the subjects in which the Jesuits excelled. This is based on a study of Antonello Romano in a period of 1610 to 1670. The subjects taught. Geometry is still the main topic, and it changes. Algebra was in the beginning period almost not discussed, but became more important later on. One of the texts we have, which gives a good idea of the material being taught, is a book by Jan Siemens, a Flemish Jesuit who studied in Antwerp and moved to Louvain later on and taught mathematics himself. And it's called The Mathematical Disciplines. And it really well reflects this organization. It starts, for example, this is the first week of October. He presents the subject of geometry by an argumentum, then follows the lectio, and then he gives a number of problemata which had to be treated by the students in the disputationes. And the fourth week of the month is left open for these public discussions. The subjects he dealt with are really wide. They start from arithmetic and geometry, but then he moves to hydrostatics, hydraulics, and in April he gets really heated up with fortification, military machines. He was fascinated by military machines, and he decided he wanted to go to a mission also in China, and he was sent to Portugal. That was typically in preparation for this mission. But in Portugal, he got involved with the military and started working for them. He was expelled from the order for doing so, and he designed the fortification of the city of Olivenza. But during the fight, he was captured by the Spanish and put to prison. He could talk to the Spanish and started working for them. And he planned a siege on the city for which he designed a fortification, so the weak spot. However, the Portuguese spotted him and killed him in battle in 1648. Several chains were then established following the Ratio Studiorum. It starts in the smaller cities like Avignon, La Flèche, Pont-à-Mousson, and then only later on we have a professor of mathematics in Paris, Reims. Also in Flanders we have Gregorius de Saint Vincentius was teaching then, and Louvain we have Boelmans and Siemens. I will say a few more things about the University of Pont-à-Mousson, which is now a lyceum. Those of you who were at LMPS a few years ago in Nancy, we had a dinner just across this university at Pont-à-Mousson. I traced the several teachers who have been teaching there. They were usually young Jesuits who are often still in their own theology degree, studying for theology after their philosophy studies. And there was a high mobility. They were sent to several colleges all over France. One factor of stability here is Jean Le Richon, but probably the best known as a mathematician is Jacques de Billy. Jean Le Richon also wrote a book which reflects very well the subjects being taught at these colleges. It's called Selecta Propositionis, a very small book, 36 pages, very terse Latin text, with just listing a number of propositions in arithmetic, geometry, mechanics, optics, music, and cosmography. And this book was appeared in 1622, but was reprinted again for the occasion of the celebrations of the canonization of the two founders of the Jesuit order, Ignatius of Loyola and Francis Savier. These celebrations took place at all Jesuit colleges in Europe, but even outside of Europe. And they took 10 days of festivities, including disputationes, including mathematical discussions for a large audience. And we have a witness account of this by Louis Wapi, who wrote a book about it, which was translated in French. And we had masses, sermons, processions with chariots, depicting all kinds of historical scenes. There was a doctoral defense, they had fireworks, and they had these disputationes on mathematics. Here's an example of a doctoral defense he commissioned a friend of Metz to open fireworks on the Mousson River. Now, And there's a recent study by a Jesuit himself, Joseph O'Keefe, who calls it the pedagogy of persuasion, the embedding of learning in rituals, allegories, symbols, and the public nature, the theatrical aspects, and all this to let people, especially from nobility, to acquire a taste of scholarship. And it worked. Some of them came to follow university for 1 year or 2 years, not getting a degree, but at least they learned something about science and mathematics. Now, out of this grew a book called Recreation Mathématique. It's often attributed to Le Richon, but I've been working on this for a few years now, and I've reached the conclusion that it's compiled by its printer, Jean-Pierre Anzelin, who collected all this material, probably from texts from students, and compiled it into a book. And it compares very well with the propositions of the Selecta Propositiones. This book became hugely popular. It went through 70 French editions over a period of 200 years. It grew out to 4 volumes. It was translated into English, Dutch and Latin, but even other works in Italy and Germany are depending on this book. The whole area of recreational mathematics grew out of this. And now for the rest of the time I will try to explain how they used they materialize mathematics as a way of turning it, making it more comprehensible for a large audience. So they wanted to turn the theoretical into practical by simplifying the complexities of mathematics, sometimes by rule of thumb or mnemonics. But interestingly, also they made it tangible. They made it like more experiments, which was also known in the magical tradition or the Archimedean tradition in the 16th century. So this physicalization had a didactical purpose to make it more understandable and easy for students. And let me give some examples of that. In geometry, it's quite easy to do something like this. So these are figures cut in cardboard or wood or something, geometrical figures, and then you have solid bodies like a cone, a pyramid or a cylinder, and you have to pass them through these openings. For example, if you pass a cylinder obliquely through an opening, you get an ellipse to do that, which is of course a conic section. So this is a way to make conic sections more tangible. And this description from the Recreation Mathématique comes directly from one of the propositions by Le Richon. He describes exactly the same thing. So it was apparently used also in these classes. Another example is to draw an ellipse. Take a glass bottle and wrap paper around the sides, and then with a compass draw a circle on it. But of course you don't put it on a plane, you get what he said, an ellipse. Now, Claude Midoche wrote a commentary on this book, which was published by himself in 1630, and he's quite critical of the author, that he doesn't understand the difference between an ellipse and an oval. But this becomes an interesting problem if you go further. It's an intersection of a cylinder and a sphere. Given the opening of the compass and the radius of the cylinder, what are the conditions in which this becomes an ellipse? And this trivial exercise suddenly becomes an interesting mathematical problem. Another example is, it's also part of geometry in the Selecta Propositiones, but it's more kind of geometrical optics, in which the game of billiard is used to apply the rules of geometry. Like the angle of incidence is equal to the angle of reflection in geometrical optics. These kind of things are discussed here, and they are presented by using the game of billiard. And we also find this in the Recreation Mathématique, the different ways, reflection to a wall, reflection between two balls, and trying to determine which direction the ball will go. This was taken up further by Marquis in the Czech Republic to determine the laws of collision. And here you see one of the first depictions of a billiard in the 17th century. It wasn't played with cues, but with a kind of hockey stick. And later in the century it was replaced by cues. And he makes a full analysis of the geometrics involved in billiard. This is the frontispiece of his book, and you see a billiard table prominently present at this cover. But not only geometry, also arithmetic was made more tangible in several ways. Here is an application of summation of geometrical progressions to population growth. This is the first practical application of mathematics in population growth. We find it in Le Deschamps' book, a proposition on optics. It was also copied anonymously by Mersenne without acknowledgement. We find it in the Recreation Mathématique. Another example of tangible arithmetic is this cryptical proposition in Le Deschamps. It is necessary that two men have the same number of hairs, écus or other things as each other. That's all there is in it. Anyone has any idea what this is about?
Physical.
Right, Pigeonhole principle. This is then better explained in the Recreation Mathématique. If you have more men in Paris than the largest number of hairs on any of them, then there must be at least two men with the same number of hairs. It's a logical principle which is used in discrete mathematics and computer science. It's taught in courses today, and it's attributed to Dirichlet, 1842. But it appears in this book. And
so this formulation appeared in that very...
Right, about hairs. So it's placed, it's like a physical necessity. It's presented like a physical necessity. I wrote an article about this in Mathematical Intelligence. Other ways to make arithmetic more tangible is card tricks. It contains a large number of card tricks. This is a well-known trick with 15 cards. You have to think of a card and say which row it is. Then you rearrange the rows, and after 3 times you can determine which card it is. You need some arithmetic, and this is a way to make arithmetic tangible. It goes back to a book of the late 16th century. Another is divination of a permutation. You have 3 objects and 3 people, and these 3 people must choose an object without you seeing it. But at the same time they have to take a number of counters. And then you come back into the room and you can immediately say which object was taken by which person. Based on the number of remaining counters. There are only 6 possibilities, given 24 counters, 3 persons, 3 objects. And you have to remember this by heart, and then you can immediately see the permutation. Again, this is something which leads to interesting mathematics. It's discussed in a recent book by Percy Diaconis and Ron Graham, Mathematical Magic, and it's called the Bruin cycles. And you have many other things. I just mentioned this one, you probably know, which is kind of combinatorics, division of casks. You have to change the liquid to get a certain amount of liters. So what we see is that mathematics has been made more accessible by physicalizing mathematics. And this has an important consequence. The dominant view of the scientific revolution is that it's a mathematization of natural philosophy, applying the laws, the mathematics to the laws of nature. However, there's a new interpretation by people like Gaukrocher, Schuster and Dupré, that it's the other way around, that mathematics was transformed, was physicalized to deal with problems of natural philosophy. And one example of this is Descartes' explanation of the rainbow. He uses precisely these billiard balls to present a theory of color. If you have refraction between 2 media, his explanation is that these corpuscles start acting like balls in tennis or billiard, in which you have topspin, which causes the ball to rotate more than needed for the rotational movement, and then you get the color red. Or you can have a slide in which the movement is less than the rotational movement, then you get blue light. If it follows the rotational movement, you get white light. That is his corpuscular explanation of light. And actually I have been able to point 5 different physical models which he uses in his explanation of the rainbow, which go back to the book Recreation Mathématique, which he knew quite well. And he even says so that in his work, in his discovery, experimentation, and also in his explanation, that he often refers to human contrivances, artifacts which helped him to discover new things and to understand nature. So this brings me to my conclusion. Mathematics education was very important for the goals of the Jesuit order, to convert people to Christianity, to go outside of the colleges and universities. They did so by popularizing mathematics, and the popularization was through a physicalization, making mathematics tangible. They had an important influence on natural philosophy, which is maybe still underestimated today. Thank you.